we haven't interested in the individuals. So the first concept, or I'd just like to discuss the first concept, the fluctuations here. The bees exploit the 4 basic rules to create an order or a structure using local and global levels of fluctuations in their collective computational efforts. The fluctuations represent the randomness function of the colony, both in local and global levels. The global level of fluctuations in domain A creates potential solutions. So the local level of fluctuations create convergence behavior through randomness, Darwinian positive and negative selection procedures. These 2 concepts are new for the Bayes algorithm. I'm proposing it now. So while positive selection keeps the direction on course, negative selection purifies through purging variations that may cause deleterious effects on the fitness of the function. So these 2 concepts are basically plays key roles in the local level of fluctuations. So in the Bayes algorithm neighborhood search, as we call it NGH, maybe many of you familiar with, that we proposed it back in 2006, I think. Neighborhood search is performed randomly with a predefined initial patch size for all selected sites. In the original version of the Bayes algorithm, we published as a technical note in 2005. So you can go and check the general structures of it. A version of the Bayes algorithm, a uniform random distribution, is used to send. And so we had the fixed patch sizes at the time, send bees to a selected site for local search. And initial patch size is set to define the boundaries of the local search, and the bees are sent into the search space. To improve the solution quality and performance, a proportional shrinking method was introduced. This new method adds another user-defined parameters to the algorithm. So my suggestion was at the time and now is the Gaussian distribution is introduced to overcome these vulnerabilities of the algorithm by eliminating the shrinking procedure. So we don't have to actually shrink the patch sizes by just introducing a Gaussian random field to the these local fluctuations approach. So randomness achieved through 2 ways, basically. One is a fixed field neighborhood randomness around the selected solution. So we have a fixed neighborhood, and instead of like a gradual decrease, I'm proposing here is a Gaussian random field. So that's another key point here. The fixed neighborhood randomness around the selected solution can be defined as this. So that's basically a random function around the plus a and minus a area of x. So that's called of course that's these numbers are supposed to be real numbers. This fixation happens to be a fixed field around the solution in a random a. So that's the fixed one. So Gaussian random field based on the Gaussian theorem of this function, whereas x is a normal distribution with a center and a standard deviation. So I modified this a normal random variate generator. So we can actually design a controlled neighborhood search by just using these Gaussian fields. So where, as you can see, this x IMR is the position of a recruiter B in the ith dimension. This x IM is the position of a selected B in the ith dimension. PD is a new concept here. I call it a patch density. Y is a normalized random value generator between 100 to 0 to 100. So this will create us like a random field. I'm just going to be presenting the results in my chapter, so you can go into the details. And if you have any queries or questions regarding this, you can actually direct it to me via email. So I don't want to take your time with the details, but it is working quite fine and well. Okay, that was the fluctuation concept. So just try to bring together these concepts under fluctuations as it happens in the collective computation model. The structure, basic assumption of the structure implies that they emerge as a result of simple interactions at lower level following simple rules. The idea of swarm intelligence is essentially constructed upon positive, negative feedbacks, interactions, and randomness, as you all know. The bees exploit all these four basic rules to create an order or a structure using local and global levels of fluctuations in their collective computational effort. However, basic assumption in collective computation gives us a different perspective. It implies that the lower level components has also high complexity level, and the model should include their level of complexity to create a comprehensive approach. If we want to create a comprehensive mathematical model, we should add their complexities into our model. So that's the basic difference, the main difference, what I'm proposing in terms of the structure here. So instead of following the swarm intelligence idea, which generalizes the model, I'm suggesting the collective computational model, which actually deploys the potential of the complexity of each individual in the system. So that's the main difference here in terms of the structure. So I'd like to propose the change for a population concept. So the population concept should be altered with individuals, basically. The bees, like any BI, and they must have their complexity represented in the model. So instead of population, we have the bees as individuals. Sorry.
I'm sorry, Dr. Koç, you have 1 minute left.
I am just collecting everything. Okay, each bee must have all the features represented on them, otherwise the system will not represent real dynamics of the emergence behavior. So each bee will have a global bee, local bee information, and random information. These three pieces will be creating our individuals in our system. So we are missing also the concept of time in our models. So I'm adding the concept of time into our models, which I call it age of bees, yaz, as happens to be in Turkish. So in real bees, there is one very important part. So that's the time. I'm adding this as the age of individual bees. So these age information will be creating another dynamic in our system, which is balancing locality and globality levels of the system. So another thing is the information increase. That's one of the key point here that we are using under the concept of Wegeldans. So it needs to be also added into the system in terms of information increase. Positive feedback for each bee I'm just representing here and using both the terminologies for local bees for fixed and Gaussian field. Darwinian positive selection applied to create representatives for information increase in the system. So that's the positive feedback. Negative feedback, basically Darwinian negative selection for remaining bees. If saturation levels exceeds, then abandon any neighborhood here. And the stop signal, I'm also adding this function into the system as a negative feedback. So interactions also, local level interactions were considered as simple. On the other hand, new studies show that these interactions are already very complex and underrepresented in the models. In the study of various iteration models will also be evaluated. So this is the basic algorithm. Not going to just going deep into the system since I'm running out of time. So the basic model will be like this one, and the mathematical model will be deploying the basic concepts of these several behavioral models, shall we say, yeah. So the rate of nectar forages, where the first term is the rate that the hivebees become nectar forages, and the last term is the rate that nectar forages die. So that's basically a differential equation based on the time. So that's what we need to be implementing into the system. So I'll be presenting the results in terms of applications and other things in the chapter. So please refer the chapters once we publish it already. So thank you, and I hope I haven't run out.
Hello, dear participants. My name is Osman Acar. I am working for Selçuk University in Turkey. In this session, I will present the effect of harmony memory integration into Bayes algorithm. In the beginning, I would like to thank Professor Fan and his group for the invitation to this organization. I also would like to thank Professor Kalyonju for the course titled Optimization Techniques during my PhD. I must clearly express that this presentation includes some part of my PhD dissertation. However, I did not include my supervisors because the effect of harmony memory integration into Bayes algorithm was studied separately. The content of the presentation consists of optimization problem, constraints, the algorithms, and results. Optimization of spherical four-bar mechanism for robotic gripper design was considered as case study. A spherical mechanism is characterized with intersection of all revolute joints in one central point. In the figure left side, a coupler of spherical four-bar mechanism with random link lengths traces a trajectory in the form of spherical curve. If this mechanism would be used to design a three-fingered robotic gripper, the object to be grasped would rotate, which is an undesirable case. Therefore, the link lengths of the mechanism must be investigated to obtain a longitudinal trajectory, as shown in the figure right side, which is bigger than 90 degrees. The longitudinal trajectory is named as a great circle arc in the spherical geometry. In other words, it is a spherical curve with zero geodetic curvature. The geodetic curvature means curvature of spherical curve projected on a tangential plane. Briefly, a spherical mechanism shown in the figure right side would be appropriate to balance an object under three force effects. A planar mechanism providing a trajectory with zero curvature can be designed by using Ball and Burmester theory, contributed between 1960s and 1980s. This theory consists of Ball and Burmester polynomials, which are composed of instantaneous invariants of the motion. Instantaneous invariants are high-order derivatives of velocity. My supervisor, Professor Ziya Shaka, derived Ball and Burmester polynomials for spherical kinematics. In these equations, E, D1, D2, D3, D4 are the constants of Ball polynomial. And omega x2, omega y2 are the instantaneous invariants of Ball polynomial. E6, A6, A5, A4, A3, A2, and A1 are the Burmester polynomial constants. And omega x3 and omega y3 are the instantaneous invariants of Burmester polynomial. Omega x1 is the common instantaneous invariance of the polynomials. C is the pseudo parameter. For a trajectory with zero curvature, the polynomials must have at least 4 real common roots. And the determinant of Sylvester matrix composed of polynomial constants must be 0. Therefore, the instantaneous invariants were searched between -25 and +25. The determinant of the Sylvester matrix is added into constraints to eliminate improper invariants. And for common real root condition is also added into the constraints. Additionally, the link lengths are limited with 90 degrees to prevent similarity between the robotic fingers. As you can see here, there is a sample spherical four-bar mechanism which has links with higher dimensions than 90 degrees. This kind of spherical mechanism cannot be placed around a sphere symmetrically. We cannot design a three-fingered robotic gripper. The Grashof laws are used to eliminate and classify the mechanism based on types such as crank rocker, double rocker, and double crank. Transmission angle is also limited to 40 degrees for meaningful force transmission. I added harmony memory into this algorithm to increase the number of better instantaneous invariants, so that I developed the procedure of harmonic Bayes algorithm, as shown in the right side of the screen. The essence of my presentation is the integration of harmony memory, which is inspired from just few. As you can see, there are 3 music instruments, and there are 3 production ranks. Each music instrument produces a note to synthesize harmonic sound. In each rank, as you can see, the notes are exchanged between music instruments. And each rank include an evaluation cell, which records the aesthetic quality of harmonic sound. Based on the aesthetic quality, the column of evaluation cells are ranked so that the harmony of sound is converged to the best values. By integrating this harmony memory right after the production step of the algorithm, as you can see here, I targeted to shift the produced instantaneous invariant values between this rank, between the cells, so that I checked the result. Now, let's look at the results. The first one is crank rocker type of spherical four-bar mechanism. These two figures are one of the results belonging to crank rocker type of spherical four-bar mechanism. This one in the left side is the result of B's algorithm, and this one is the result of harmonic B's algorithm. The result of B's algorithm has a curvature enough to be used for gripper design. However, harmonic B's algorithm has lower geodetic curvature value. As you can see in the figures, the result of harmonic B's algorithm traces a trajectory which is very close to a longitudinal path. In the case of B's algorithm, the trajectory is not good as harmonic B's algorithm, but it can be used for gripper design. Consequently, the dimensions of both results are very risky because they can cause singularity between gripper fingers. The second results are in the type of double rocker spherical mechanism. The dimensions of the trajectory is same in both of the algorithms. However, the curvature value of B's algorithm result is higher than the harmonic B's algorithm result. In the figure right side, the curvature of coupler point traces a trajectory. In the figure right side, the curvature of coupler point trajectory is very low in the beginning of the motion. However, the curvature value increases as the coupler point approaches the pole of the spherical plane. In the figure left side, the trajectory of coupler point crosses the expected longitudinal path. Both of the mechanism link lengths are proper to design a gripper. However, only harmonic B's algorithm result is completely useful. The third results are in the type of double crank spherical four-bar mechanism. The harmonic B's algorithm has lower geodetic curvature. As you can see, the trajectory between 1 and 2 is almost longitudinal. However, in the case of B's algorithm, both the curvature value and the link lengths are very high. Consequently, the best mechanism for robotic gripper design is the double rocker mechanism. This is the CAD model of the gripper, which is fingers are designed from spherical double rocker mechanism. This is the top view of the prototype. The curvature of coupler point was measured by using endoscopic camera on the top of the prototype. One of the fingertip was remarked by red color, and the camera recorded the motion of the spherical mechanism. The recorded video was processed and coordinates of the red colored points are recorded. Therefore, the curvature of the spherical mechanism was calculated by using parametric curvature equation. This is the figure of measurement results comparative to optimal solutions. The blue colored graph is from optimal solutions by using algorithms, and orange colored graph is measured values by the experimental stage here.
Hello everyone, I'm Semih Cakiroglu. Welcome to my presentation. I will introduce to you a tool for PID tuning, indeed, that uses a multi-objective B algorithm. It's developed by my colleague Murat and me. As you see in the agenda of this page, I briefly deal with some PID tuning methods which we have referred. Next, the idea and basic items of optimization-based tuning will be shown. Then, multi-objective Bayes algorithm is planned to explain as a technique of our tool. And finally, the major properties and capabilities of the tool will be discussed with a comparison. If we start to have a look at PID tuning issue, probably the most known method can be assumed to be Ziegler-Nichols. But let us talk about the plant which we want to control. For most of the robotic applications, the system can be defined as linear or can be linearized. For instance, we have considered a joint of a robot arm as the plant to be controlled. To apply Ziegler-Nichols PID tuning method via step response, there are several parameters to know about the system. And as you see on the right side of the screen, the steady-state value Km is around 0.93. The time tau m, where the rising slope meets the zero line, is around 2.46. And the difference between Tm, which is the time rising slope crosses Km line, and tau m is found as 16.54 seconds. Generally, Km is used in other Ziegler-Nichols related methods. Therefore, if we calculate Kp as 1.2 times of Tm over tau m, and Ti as 2 times of tau m, and Td as half of tau m, we get these PID parameter values, which results with such a behavior. You can notice that there is an overshoot nearly 15%, and it settles in approximately 100 seconds. Let's evaluate PID tuner of MATLAB, which is already getting used widely. It seems pretty compact. You can handle some adjustments and obtain the tuned controller parameters. The adjustments are also related with the objectives of the controller goals, such as response time and robustness. This interface uses an optimization-based code in background, in fact. Since the issue is an optimization problem, we have parameters to be optimized, which are the controller values Kp, Ki, and Kd. Then we construct a cost function related with the closed-loop response of the plant. It can be the integral of absolute error, or a stronger version called as integral of square of error. At last, we may define the constraints of the problem which limits our search area. These can be a range of parameters, bandwidth and settling time, and etc. And the algorithm part aims to minimize the cost under consideration of constraints. There are mainly two kinds of search method. One of them is gradient-based search, which involves math. Since it's a derivation operation, there are some assumptions to get a unique solution. Probably the most crucial rule is about convexity, which means the derivative of cost function should satisfy a unique zero point in the search area in order to be sure on global minima. The point is convexity and complexity of the mathematical model might be challenging. The other one is derivative-free method and provides with heuristic approximations. There is a biomimetic behavior on the search style, and this is the method that we use in our tool. There are two items to explain in this part. The first section is the multi-objective concept. Our main goals to satisfy are minimum steady-state error, overshoot, settling time, and maximum bandwidth in the defined range. In the algorithm, the cost function has been constructed by weighting the objectives by related gains, which are tunable by the user via interface. The first two goals are related with the robustness, and the following two goals correspond to the speed of the system. Therefore, we have used common weights for the related goals. The second section shows the flow of the main algorithm and search part. Since we use B algorithm, there is a defined B population which includes elite Bs, selected Bs, and their regions. At the first step, the population is randomly placed, then the cost is calculated and sorted. Local and global searches are stated regarding the cost sort. Finally, results are evaluated to be renew the search or terminate the optimization. On each search, closed-loop transfer function is evaluated due to the system characteristics contributing to the cost function. If we have a look at the interface of our tool, there is a section where you can define the transfer function of the system to be controlled. Besides, there are sliders to set the objective weights. Also, you can find several boxes to bound the parameters to be optimized. On the last panel, the user can manage the optimization parameters related with the P population, iteration number, and search area. On the other hand, you can observe the change on each iteration. At last, the values achieved are listed when the optimization process has finished. As a comparison, there is a plot of step responses of same plant with each controller tuned via listed methods. We can throw out that our tuner provides with satisfying results. Truly speaking, it takes a little bit time, like not in minutes but in seconds to proceed the iterations. However, it's not a big concern since it is an offline procedure. On the last slide, you can find a different sketch for a different set of adjustments. By choosing a more robust system, we achieve a less overshoot on the response. Thank you all for listening to my presentation.
Hi, firstly, let me introduce myself. My name is Shafie Kamaruddin from International Islamic University Malaysia, or IIUM Kuala Lumpur, Malaysia. I am the presenter in this workshop. The title of my project is Optimization of Surface Roughness in 3D Printer using the BEAST algorithms. Before we move forward, these are the content of my presentation. In this presentation, I will start with a brief introduction or background on this project, then problem statement followed by objective of this project, methods, result and discussion, and lastly the conclusions. So what are these projects about? So this project focuses on the 3D printing technology where it creates a product layer by layer. I'm sure most of us know what 3D printing technologies. So it is quite well known nowadays. The printer that we're going to focus on this project is known as Fused Deposition Modeling, or FDM, which use thermoplastic as the material. So what are the issue with this 3D printing? One of the main issue in this 3D printing is rough surface textures. To control the surface roughness, we can control the parameters. There are 4 parameters for the FDM machine that we are using. The first one, the parameters are layer thickness, print speeds, print temperatures, and outer shear speeds. So how we can control the surface roughness. In order to control the surface roughness, we need to control the parameters. So how to obtain the right combination of parameters? The conventional way of dealing with this issue is by experimental testing, where we print it and we check the surface roughness. However, this method is time consuming and also quite costly. Thus, these projects focus on implementing optimization algorithm known as the BEAS algorithm. So the objective of this project is, first, we want to apply the BEAS algorithm for optimization of surface roughness in 3D printer, or specifically FDM. Then we want to compare the predicted results with results of others algorithms that are available in the literatures. Then we also want to verify the predicted result by comparing with the experimental 3D printed model surface roughness, meaning once we have obtained the best combination parameters using the BEAS algorithm, we're going to print that part using the parameter that we have found or obtained. Then we're going to compare the experimental with the predicted result. So that's what we're going to do. What are the objectives of this project? Then what are the methods that we use? First, we are using a software known as R software to run the BEAS algorithm. So we're going to do the coding in R software. Then we are going to use regression model of the surface roughness obtained by Saad 2019 as the fitness function. So we use this regression model as the fitness function. Then we set the parameters for the BEAS algorithm. Then we run the BEAS algorithm for 50 runs. Then number 6, we compare the predicted surface roughness. So we run it for 50 run, and we take it what are the best surface roughness found by the BEAS algorithm. Then we use that to compare with surface roughness found by others algorithm available in the literatures. So next, this is what we're going to do. We're going to verify the predicted surface roughness with experimental surface roughness. So we're going to do this next. So this is a comparison of result found by others algorithm with the BEAS algorithm. So we can see that we take it the best surface roughness found over 50 runs, and we record it in this table. So based on the result in this table, it is found that the BEAS algorithm obtained surface roughness slightly better than RSM. So RSM is result obtained by response surface methodology. So we can see that it is slightly better compared to RSM. But if you compare with PSO and an algorithm called SOS, or symbiotic organism search, is not that far. So we can say that it found quite a good result. then this figure shows convergence of the BIS algorithm. So we can see that the trend is going toward the minimum up until end of the iteration. And these figures actually shows the performance of each process parameters and the plot function diagram of the BIS performance of each process parameter and the plot function diagram of the BIS algorithm respectively. So it's showing the progress of each parameters. For this, the first figure is on layer thickness, then the second figure here is on print temperatures, then this one is on print speeds, and the last figure is on outer share speeds. And you can see the progress when it searching for the best solution of each of the parameters. So in conclusion, we could say that we have implemented, or we have applied optimization algorithm or BIS algorithm to optimize the FDM parameters. Then we also found that the optimization algorithm found better predictions than conventional RSM or response surface methodologies. And in the futures, we could extend this to others additive manufacturing processes, because in additive manufacturing we have many types. So we could also extend this to others application as well. So I think that's all from me. Thank you very much. If you have any question, you can always ask me in the Q&A session after this. Thank you very much.
Hi, I'm going to present a study on a shape recognition in point cloud scenes. This is work of my doctoral students, in particular Luca Baronti. So the idea is that the shape of many mechanical objects can be approximated using geometric primitives like cylinders, cones, boxes, etc. This is very important for robotic manipulation, because once we know the shape of an object, we can decide how to pick up the object, so the grasping points. This study is part of a wider project, the PSSC-sponsored Autoriman project, which is on robotic disassembly for remanufacturing applications. So the primitive fitting problem is basically to fit a geometric primitive to a point cloud scene. Point cloud is basically a 3D model of environment of a scene, and it can be acquired using some laser scanner, some depth camera. You can use a cheap Kinect or some very fancy and expensive camera. It's very common, it's becoming more and more common in machine vision, because the availability of laser scanners is becoming quite easy, quite wide. It's, as I said, it's often intermediate, if not one of the first steps in robotic manipulation, like robotic grasping, and state-of-the-art solutions rely on knowledge of the scene. So, for example, the most popular method at the moment is the Ransack algorithm. In the Ransack algorithm is the need to set a sort of tolerance for the position of the points. So basically, we need to know more or less what is the level of noise in the scene. Now, this is an example of a primitive fitting problem. Here you have a scene with two shapes, a box and a sphere. Here you have another example with a cylinder. These are all nice point cloud with no noise, nothing. There may be point clouds of much worse quality, where there is, for example, some background noise, this kind of speckle noise that you see here, or there can be imprecision on the location, basically of the object, so you'll get this kind of blurry image. Or you can have both. In this case, fitting primitive to something like this is extremely difficult. Now we decide to approach this problem as a numerical optimization problem, and then use the Bayes algorithm to solve this problem. Now you all know the Bayes algorithm. I don't need to explain you what is the Bayes algorithm. You are here the workshop for the Bayes algorithm. We'll just explain you the two bits that are necessary to basically adapt the Bayes algorithm to this particular problem domain. The first is the encoding of the solutions, the second is the fitness function. So in this case we have the different shapes can be encoded using different number of parameters. So we can't have just one Bayes algorithm, we need 3 Bayes algorithms in parallel, each one trying to fit a particular shape to the scene, to the point cloud. So in this case we just studied 3 cases: sphere, box, and cylinder. Fitness function looks kind of complicated. It is not. It is basically a ratio between NC and delta, 1 plus delta. Now NC is the concordance of the normals, so the normal to each point and the normal to the closest surface to the point, the closest surface of a candidate solution of a primitive. Now if there is full concordance, so if this primitive is a perfect match to the point cloud, then the concordance of the normals will be equal to 1. If instead the match is terrible, so for example the candidate solution is perpendicular to the solution to the point cloud, then the function NC will be equal to 0. The second delta is the distance between each point of the point cloud and the closest surface on the primitive. Distance will be 0 in case of a perfect match, or something greater than 0 in the case of a non-perfect match. Now, said this, you can see that the fitness function is equal to 0 if there is really a poor fitting, so there's no concordance absolutely of the normal, and the delta is verified. In this case, the numerators will be equal to 0, the denominator will be greater than 1. So fitness function will be equal to 0. If instead normals are perfectly concordant, then numerator will be 1, denominator delta will be 0, there will be no distance between the point and the surface, so the denominator will be 1. So 1 over 1 is equal to 1. So we have the fitness function basically varies between 0 and 1. So primitive fitting now boils down to a function maximization problem. And here we know that the Bayes algorithm is really good at solving this kind of problems. So the rest of the Bayes algorithm is the standard Bayes algorithm. The only thing I need probably to explain a bit better is what is the sampling coverage. Basically, we wanted to use this algorithm on real-time applications, so instead of using all the points of the point cloud, we just fit the primitive to a percentage of the points. This percentage was randomly picked. Now, we compare the performance of the Bayes algorithm to RANSAC and an evolutionary algorithm. In the case of the evolutionary algorithm, we parameterize the evolutionary algorithm in order to give it exactly the same sampling opportunities as the Bayes algorithm. So in one run of the algorithm, the evolutionary algorithm performs exactly the same number of function evaluations, so it tests the same number of candidate solutions as the Bayes algorithm. Here you see how the Bayes algorithm works. Here you have, for example, a set of candidate solutions. On the left you have the case of a box, on the right you have the case of cylinder, so you can think of these all the best sides. So these are the candidate solutions. Each one associated to one of the best sides. And then the B's algorithm will start working until these shapes will approach the real shape, the point cloud, until at the end the best, so the global optimum, will be the shape that fits perfectly the point cloud. Now we did tests, as I said, we compared the performance of the B's algorithm and evolutionary algorithm and RANSAC on 3 datasets. These 3 datasets in reality are one dataset with more or less the same number of samples of spheres, boxes, and cylinders. The difference between the 3 datasets is the level of error. Clean means no error. Error means that we perturbed the points of 5%, and double error means that we perturb of 10%. So basically, the difference between these 3 datasets was the level of error. Now you can see the results on the detection of spheres. You can see that the B's algorithm performed best when there was a certain amount of noise. In the case of a clean scene, RANSAC performed slightly better. If instead in the case of boxes, we had the B's algorithm outperformed in all cases the other 2 algorithms. In the case of cylinders, instead the best performing algorithm was RANSAC. Now what we can say first is that trying to solve a primitive fitting problem as an optimization problem is a good idea. We have seen that the evolutionary algorithm is never a contender. However, the B's algorithm performed at least as good as RANSAC. In one case, in the case of boxes, the B's algorithm performed always better than RANSAC. In the case of spheres, performed better in the 2 cases where there was noise, and in the case instead of cylinders, the best performer was RANSAC. So we can say that at least there was a draw between these 2 algorithms. Also, the B's algorithm and also the evolution algorithm were robust to perturbation of the points. So when noise is introduced, there is no variation in the performance of the 2 algorithms. And the main difference between RANSAC and the B's algorithm, that in terms of accuracy are the 2 winners of this comparison, is that the B's algorithm doesn't rely on any specific assumption on the scenes. For the RANSAC algorithm, we had to define a tolerance threshold. Now, if you want to know more about the details of the study, we published a paper recently. If you want to use this tool that to create primitive geometric primitives and inject noise in the point cloud, Luca Baronti made this tool available on GitLab, so you can perfectly reproduce our experiments or your own experiments. And with this is everything. Thanks for the attention. I'm sure in the live version there will be a lot of questions. Bye-bye.
Hello, I am Engineer Mariam Kashkash. I have a master's degree in Artificial Intelligence from University of Aleppo, Syria, and I am working as research assistant in the University of Sharjah, United Arab Emirates. I will present a webinar about solving robot path planning problem using the Bayes algorithm. The main outlines are path planning definition. After that, I will propose a modified version of the Bayes algorithm to solve this problem. I will go through configuration space, initialize the population, local search and global search, and finally I will discuss the results and comparison with other algorithms. Path planning can be defined as a process to find an obstacle-free path between a predefined start point and a predefined goal point for a mobile robot. We propose a configuration space method to represent the environment. In this method, the environment is a continuous. The configuration space is consisted from C free and C obstacle. C-free is the area in which the robot can move without collision with any obstacle. C-obstacle is the area where the obstacle exists. In order to represent a mobile robot as a point, the obstacle area is inflated by additional area which is proportionate to the robot radius. The proposed method is illustrated in this diagram. The inputs are map, the environment, S, the start point, D, the destination point, NGH is the size of neighborhood. The main parameters of the BA are generated randomly using uniform distribution function. Next, a new method to build the initial population. After that, the main loop of the Bayes algorithm is repeated through local search and global search until the length of optimal path doesn't change on a number of iterations. Finally, the best path is returned. Now, initialize the population. At the beginning, add the start point to the initial path. After that, generate a new rotation angle. Theta is generate a new rotation angle theta by uniform distribution function in the range 0 to pi. Next, compute how much the robot can move based on its sensor range and add the new point to the path by calculating its coordinate as following equations. In the case of the robot cannot move to any new location, by that theta, a new theta is generated randomly. After that, repeat the previous steps until reaching the destination directly, without any intersection with an obstacle. After that, the stage of path shortage. Path shortage is implemented by removing the intermediate point between 3 points if the direct connection line is available. Here is an example of full initial path for this map. This diagram illustrates the process of finding new initial path. This process is repeated until finding n initial paths, where n is the population size. The B is an initial path, which is represented by a sequence of points and the evaluation value. The number of points in the B is k, and each B can have a different number of points in the same population. Now the evaluation function. We use the Euclidean distance as evaluation function to calculate the evaluation value, and our goal is to minimize this value. After that, the local search. The m good B's in the population are selected based on their lengths, and the elites among them are determined. NEPBs are called to search locally in the neighborhood of the elite passes, and NSP for remaining m-e good bits. However, NEB should be greater than NSP. The local search is implemented by generating NEB or NSP coordinates in the neighborhood of the points of the former path. The coordinates are generated using uniform distribution function, and this process will lead to a number of new paths. However, new path is stored as a member of the population in the case of its length is smaller than the original path. Otherwise, it will be ignored. Global search is implemented by sending the remaining bees to find new solutions to maintain the diversity in the population. Next slides show the evaluation of the obtained path through the main loop of the bees algorithm. The first iteration begins with path lengths of 50.3663 meters. The solution is improving through iterations. However, after about 100 iterations, the solution doesn't change and algorithm stuck with local optima. So we suggest to implement neighborhood shrinking. As following equation, we suggest to implement neighborhood shrinking as this equation, and the result in iteration 203, the solution return to enhance. The final result as in this figure. The obtained length is 39.7713 meter, and this length is the average of result of 10 implementations, and the parameters are random. Here are other results for different map, and the tables clear the random parameters. These figures show the effect of changing the parameters value from big to small. It's clear the proposed method can find the optimal solution smoothly and quickly when parameters are big. The two figures show the impact of changing M and E when N is constant. And this figure illustrates the impact of big NEP on solution evaluation. Here are some comparison results of other algorithms like genetic algorithm, BS, and particle swarm optimization, artificial bee colony, and ABACO. The comparison show the superiority of the modified bees algorithm in finding the best path. And thank you for your listening.
Hi everyone. My name is Feiying. Today I'm going to talk about the application of the bees algorithm on 3D point cloud registration problem. 3D point cloud registration problem is a process of finding a rigid transformation which aligns two point clouds. The rigid transformation consists of a rotation and a translation. The rotation is a 3 by 3 matrix, and the translation is a 3D vector. As shown in the figure, the two bunnies are geometrically aligned after point cloud registration. There are many applications for 3D point cloud registration, such as robot manipulation. The first step is to locate the object for robot grasping, pick and place. The location and orientation of the object can be aligned with the CAD model so that its pose in robot base could be determined. For example, in AutoReman project, the 3D registration could be used for robot manipulation. The point cloud registration is usually formulated as an optimization problem. The fitness function is defined as the residual error between 2 point clouds using closest point correspondences. As in the figure, for each point in the X point cloud, the residual error is the distance to the corresponding closest point in Y point cloud. The solution space for this cost function is multimodal. This means there are many suboptima. The solution space is encoded and decoded using ROUGHNESS formula, which transforms the rotation matrix into a 3D rotation vector. Thus, the rigid transformation could be represented with a 6D vector. SVD is an operation of calculating the closed form solution which aligns 2 point sets with given specific point correspondences, while ICP adopts closest point heuristics and minimizes the cost function using SVD iteratively. ICP is fast, but prone to suboptimal convergence. If given unfavorable initial solution, it may return a wrong element. This study adopts the Bayes algorithm as global search technique and integrates the SVD operation for the scout bees. The enhanced local search can find the local minima quickly. The unsuccessful attempts of stochastic local search is reduced. The global search capability is improved by the mechanism of neighborhood shrinking and site abandonment. Here is an example of 3D point cloud registration. In the experiments, 10 shapes were used for testing. For each shape, it generates 100 point cloud pairs with random transformations. For each point cloud, it has 1000 points. The hyperparameters for the Bayes algorithm is set as in this table. The budget for the iterations is 100. The convergence criteria for the cost is 0.01. The stagnation cycle is set as 10. The shrinking neighborhood rate is 0.8. The consistency measures the success rate of the algorithm. In this result, ICP has low success rate as it is susceptible to local minima. The Bayes algorithm shows high consistency, and its success rate climbs with the increasing bee colony size. The Bayes algorithm with SVD operation achieves high success rate, even with small bee colony size, benefiting from the fast local search. The precision measures the residual error of the solution. ICP could achieve highly precise solutions, but the variance of the residual error distribution is large. This implies ICP could get bogged down in suboptimal convergence. The residual error of the Bayes algorithm concentrates on a region with a small variance, means high consistency. The residual error is not low, means it could find nearly the global optima for coarse element. The Bayes algorithm with the SVD operation can achieve high consistency. Meanwhile, it can get a precise solution by reducing the residual error nearly to zero. The experiments on the datasets with noises is aimed to test the robustness of the algorithms. We applied Gaussian noises on the point data for each point cloud. In this study, 5 incremental noise levels were set for the experiments. The B colony size was set to 20 based on the previous evaluations results. The Bayes algorithm still shows results consistent with clean datasets. The success rate of the Bayes algorithm is above 90%, and the Bayes algorithm with SVD operation achieves 100%. Thus, high robustness of the Bayes algorithm to noisy data is demonstrated. In conclusion, the Bayes algorithm successfully tackles the suboptimal convergence problem for 3D point cloud registration. The SVD operation enhanced the local search, and it can identify the local minima rapidly. The mechanism of neighborhood shrinking and site abandonment improves the efficiency of search in low solution space. Bayes algorithm with SVD operation can also find the precise solution as good as ICP does. The test on noisy datasets demonstrated the robustness of global search strategy of Bayes algorithm, and is promising for the data obtained from real scenes. Thank you for your attention.
Hi everybody, I am Sultan Zeybek. I'm a research assistant at the Fatih Sultan Mehmet Vakıf University. I am attending from the Beyoğlu, Istanbul, Turkey. Today I am going to talk about the remaining useful life prediction of engines for remanufacturing using the Bayes algorithm optimized semi-supervised deep learning model. First of all, I would like to talk about the predictive maintenance. We know that predictive maintenance lets us to estimate time to failure and peak points problem in complex machinery to increase the operational safety and reduce cost. There are two common approach to make the predictive maintenance. The first one is the regression, and the second one is the binary classification problem. These data-driven models has two main steps. The first one is the data preparation and feature engineering, and the second one is the train and evaluation regression model or classification models. Remaining useful life prediction is the estimation of a component, and it is one of the most important tasks for the predictive maintenance systems. Remaining useful life is computed as the time between the current condition point of a machine and failure point. Depending on the system, this time can be represented in terms of days, months, or cycles. As it is given in the figure, we know that one of the big main challenge with preventive maintenance is determining when to do this maintenance. By scheduling maintenance very early, the machine life is wasted. That's still useful, and it adds to the cost. However, if we can predict this machine failure, we can schedule maintenance right before it. So that is the predictive maintenance, and it lets us to estimate a time to failure and pinpoints the problems in the complex machinery. In this study, we use remaining useful life. We try to predict the remaining useful life of the NASA aircraft turbofan engines, and it is the turbofan engine corruption simulation dataset, and it contains sensor values from 100 different aircraft engines for time cycles from run to failure, and 21 sensor readings for each cycle. At the figure, we can see the example of the training dataset and their features. It contains approximately 20,000 records, and the testing dataset
contains approximately 30,000 data fields, and the ground truth data contains the correct remaining useful life of these 100 different aircraft engines for each ID. The proposed prediction model has been formulated as a binary classification task and based on the semi-supervised labeling process. The figure shows how the training and the testing data is labeled. In this data, each engine is assumed to be operating normally at the start of each time series, as we can see in here, remaining useful life data field, and it starts to degrade at some point during this series of operating cycles. The last cycle in each time series can be considered as the failure point of the corresponding engine. As we can see in the dataset table, the engine ID with 1 fails at cycle 192. So, and the engine with ID 2 fails at cycle 287. We add remaining useful life data field by calculating it as following subtraction method. Remaining useful life is found by last cycle of the engine minus cycle number, and at the end of this process, we got this label 1 and label 2 as a classification model, and we use this remaining useful life information to answer the question: is this engine going to fail within W1 cycles? W1 is used as a predefined use case related parameters, which is used to label training data. For example, for work cycle 13, the labeling pseudocode is given something like this. If the remaining useful life is smaller or equivalent to this 13, the failure is labeled as a 1, or otherwise it is labeled as a 0. This dataset includes some features, and the selected raw features has been used for all of the sensor measurements from 1 to 21 are included in the training dataset, and additionally cycle and setting 1, setting 2, and setting 3 has been used. And aggregate features are used to summarize the historical activity of each asset. 2 types of aggregate features are created for each of 21 sensor values. These are given in here in this figure, and as it can be in this figure, each engine have different life durations, and the working time in the training data set could be different for each engine ID. The proposed model for this architecture is using the sequential deep learning model and LSTM architecture. And we have used 100 hidden layer and 15 hidden input layer in this LSTM model. And the hyperparameters have been used. We use 26. We use 16 different cycles, and for labeling process from 10 to 105 different recent cycles, or we can say it as a window length in LSTM model from 10 to 15. We propose the Bayes algorithm to optimize this deep learning model as it is given in the flow chart. We start with the initialization of the Bayes and performing forward parse for each pair of the data sample, and then we evaluate the fitness function, loss function, and sort the population. And we use local search, mutation operator, and global search. After that, we construct new population. And this process is continue until we converge the optimum value. In this proposed model, we use only three scout bays that combines exploration power of the BA algorithm to escape the local optima and gradient exploitation drive of new local search operators to improve the solutions. And also we continue to use gradient-based learning, the advantage of the gradient-based learning as a gradient operator for reaching the local optimum quickly. The aim is to use the strengths of the gradient-based backpropagation algorithm in the most commonly used LSTM architecture. Mutation operator and global search learning use to explorative search for potential new solutions. Here is the ROC curves and best case scenarios without using Bayes algorithm. There are some issues in these results because we can clearly observe that for some parameters there are some overfitting and test accuracy is better than the train accuracy, as we can observe. So to prevent these issues and to improve the accuracy result of the model, we propose to use BA algorithm to improve the LSTM performance by using the third combination of the hyperparameters. And experimental results of the proposed semi-supervised deep learning model is given at the table. As a training algorithm, we use ADAM, and also by hybridizing ADAM and Bayes algorithm with a mutation operator, we can observe that the F1 score is much more better than the LSTM model without BA algorithm. And also we observe that BA mutation is not better than the BA without mutation operator. Mutation operator has been used to shuffle weights of the training model as a learnable parameters. So the accuracy results show that BA with mutation or BA without mutation gives similar performance results, but the F1 score of the BA with mutation operator is better than the BA without mutation operator. The hyperparameters of the proposed model can be seen in the following table. Here are the confusion matrix of the proposed model. As we can see in the confusion matrix of the train set or test set with BA algorithm, we can see that LSTM model performed much more better than the LSTM model without BA algorithm. And as a result, we can say that remaining useful life prediction of engines for remanufacturing using the Bayes algorithm optimized LSTM model performed better. So, and mutation operator has improved the F1 score of the BA3+ algorithm. However, it has been observed that the training and the test accuracy of the BA3+ without mutation operator is better than the BA3+ with mutation operator. In the future, we are trying to improve this BA3+ algorithm with different hyperparameter combinations. And thank you for your attention and listening.